This is Jack Jackson back again, and we're going to be continuing to talk about integration and some things that we can do with that. And one thing I want to talk about in this video is symmetry of graphs and how that can help us in certain integration problems. So, for example, if a function is symmetric about the origin, and of course what that means is you have 180 degree or pi radian rotation symmetry about the origin. So if you fix the origin and rotate about the origin half of a circle, that the graph collectively ends up the same. If that's the case, then if we integrate that function over an interval of the form minus a to a, what are you going to get? Well, you're going to get 0. Here's an example. If we want to integrate from negative 2 to 2 of x cubed dx, we notice that this has origin symmetry. And you can see the graph here on the right. And the point here is that the area in the first quadrant is going to have a rotated image. In the third quadrant, one's going to be above the x-axis exactly the same amount as the other one is below the x-axis. So when we integrate across that from negative 2 to 2, in fact, they cancel each other out. And so that's going to be 0. And we were able to do that and argue that basically geometrically without having to do any kind of finding antiderivatives. And so that kind of an integral is very easy to do. Now, there's two things you have to make this work. First of all, the function's got to be continuous on that piece, or at least integrable on that piece. The integral must exist, must be a proper integral. Secondly, the function must be symmetric about the origin. And then the third thing is the limits must be symmetric about the y-axis, in other words, from minus a to a. Okay, and that integral is 0. Now remember that a function with this type of symmetry is called an odd function. Actually, technically speaking, the odd function definition is an algebraic condition that says f of negative x is the opposite of f of x. So f of the opposite of x is the opposite of f of x. So basically when you change the sign on x, you end up changing the sign on y as well. But that's exactly what's meant by origin symmetry. So a function is an odd function if and only if it has a function and it has origin symmetry. So one thing we can say is then if f is an odd function, then the integral from minus a to a of f of x dx will be 0. So what are some examples of odd functions? Well, certainly odd degree power functions are odd functions, like y equals x cubed, y equals x to the fifth, y equals x to the seventh. And that's where we get the name odd function, but it doesn't have to be specifically just an odd power function. There are many other examples. For example, the sine function is an odd function. We'll look at a few other examples here in a minute. Now, an even function is when you do f of the opposite of x, you get the same thing as f of x. And that turns out to be the same thing as a function with y-axis symmetry. Y-axis symmetry means you take the graph and you reflect over the y-axis, and ultimately what's to the right of the y-axis is matched by what is to the left of the y-axis and vice versa. And so we have a reflected image that is ultimately same. Not necessarily point by point the same, but collectively as a set of points, it's the same. Okay, that is y-axis symmetry, and a function with that property is an even function. Now, in this case, they don't. These areas don't add up. I mean, they don't cancel each other out. For example, here's integral from x to the sixth from, say, negative 2 to 2. But what we notice is this area over here in the second quadrant and the one in the first quadrant, they're both above the x-axis, so they're both going to add to the integral. They don't cancel each other out. You don't have a positive one and a negative one that cancel like we did in the odd function. But we do see that they're both the same. So what we can do is we can just say, okay, well, if we just go from 0 out to 2 and just find this part here and just double it. Now, why is that useful? Well, it's useful because when we get our antiderivative over here on the left, we'd have to evaluate our function at both a and at negative a and then subtract. Whereas the one on the right, we just have to evaluate at a and 0, subtract, and then multiply by 2. Well, a lot of times it's easier to evaluate a function at 0. A lot of times when you plug in 0, a lot of the terms go away or something. Sometimes that is helpful. And so that just makes that evaluation part a little bit easier to do. So for example here, if we compute the integral from -2 to 2 of x to the 6th, we could do that. Not the only way we could do it, but one way we could do it is to actually integrate from 0 to 2 x to the 6th and then just double it. So the antiderivative would be x to the 7th times 1/7, so it's 2/7 x to the 7th, evaluate from 0 to 2. Here I just left the 2/7 there, 2/7 times 2 to the 7th minus 2/7 times 0. And see this part where you plug in 0, that's gone, that's all just 0, so that part we can ignore. And so we end up with 2 to the 7th times 2, this is 2 to the 8th altogether over 7. 2 to the 8th is 256, so it's 256 over 7. And the exact form of that decimal is you have to divide it out till you get 6 places, and then it gets in a repeating pattern. So it's actually 36.571428, and then of course another 571428, 571428, 571428, and so forth. So when you divide by 7, you typically get a 6-digit repeating pattern. We can verify this with the calculator like this, and just integrate from -2 to 2, and get our answer and change it to a fraction, and it works out quite nicely there. Now let's talk about some characteristics of even and odd functions. The only function that's both an even and an odd function is the 0 function, f of x equals 0 for all x that you have, which would be the x-axis, either the entire x-axis or a portion of that that's symmetric on both sides, because this graph has to be symmetric about the origin, rotated about the origin 180 degrees and get the same thing, and it also has to be symmetric about the y-axis, and the only way you can get both of those things to happen and still be a function is for it to just be the x-axis. So that's a very unusual one. So other than that, it can't be both even and odd. But many functions are neither even nor odd functions. If you think about just drawing any old graph of any old function, it would typically not have any symmetry at all, perhaps, or may not have specifically y-axis symmetry, or origin symmetry. If it's a function, of course, it doesn't have x-axis symmetry unless it's the 0 function. So most functions are neither even nor odd. It'd be something special to be an odd function or an even function. And if you add a non-zero even function and a non-zero odd function, you'll get something that's neither even nor odd. Well, what are odd functions? Odd degree power functions, this is where it gets its name, like y equals x cubed, y equals x to the 5th, y equals x to the 7th. Power functions, more generally, where you put the fraction power, which is an odd over odd when you reduce it. So y equals x to the 5/9, y equals x to the 7/3, y equals x to the -3 over 1, or y equals x to the -3rd power, y equals x to the -5/9, y equals x to the positive 143 over 11. No, that reduces. 143 over 29. Okay, so that would be, all of those would be odd degree power functions. Now, some of your trig functions, 4 of them, are actually odd functions. They have origin symmetry. Sine, cosecant, tangent, and cotangent are all odd functions. 3 of the inverse trig functions, arcsine, arccosecant, and arctangent, are odd functions. The hyperbolic sine is one example of an odd function. And in general, if you add 2 odd functions, you get an odd function, or add or subtract two of them. The product of an odd function with an even function is an odd function, and the composition of 2 odd functions is an odd function. So you might think about those a little bit and see why those things would be true. The following are some examples of even functions. So even degree power functions like y equals x squared, y equals x to the fourth, y equals x to the sixth, etc. are even degree power functions. And that's kind of where it gets its name. And if you can make it into a fraction power for a power function where that fraction in reduced form is an even over an odd number, that will also be an even power function. In other words, they will have y-axis symmetry. So y equals x to the 2/9, y equals x to the 4/3, y equals x to the -6. Think of that as -6/1. Those are all examples of even functions. Two of the trig functions, two of the basic ones there, are even functions, cosine and secant. The hyperbolic cosecant, cosh, is also an even function. Absolute value of x is an even function. And the sum of two even functions is an even function. The product of two even functions is even. The product of two odd functions is even. The composition of an even and an odd function, if we do the odd function first, applying that first, is even. And the composition of any function with an even function, okay, even function applied first, that's going to be an even function. For example, any function of absolute value or any function of x squared would be an even function. Now let me prove just a few of these. I'll let you maybe provide the proofs yourself for some of the other ones. So let's let E1 and E2 be even functions. Let O1 and O2 be odd functions. And let's just let f of x be any old function. So if the sum of two even functions, E1 of, let's take E1 plus E2 of minus x. That's E1 of minus x plus E2 of minus x. Since those are even, that's E1 of x plus E2 of x. So the sum of two even functions is even. When I say selected proofs, perhaps this is just the main step of the proof. So the sum of two odd functions, O1 of minus plus O2 of minus x, will be O1 of minus x plus O2 of the opposite of x. But since they're odd functions, the minuses are brought out front, so that becomes the opposite of O1 of x plus the opposite of O2 of x. And we notice we can factor out the -1, so that's the opposite of O1 of x plus O2 of x. So that makes it an odd function. So the sum of two odd functions is odd. If you take the product of two evens, it's even. So E1 of minus x times E2 of minus x is E1 of x times E2 of minus x, so that's going to be even. The sum of two odd functions, the product of two odd functions, product there, is going to be, let's see, that's odd function 1 of minus x times odd function 2 of minus x is the opposite of odd 1 of x times O2 times the opposite of O2 of x, and the two negatives multiplied together becomes positive, so that's just O1 of x times O2 of x, so the product of two odd functions is actually an even function. And disappear there, okay. And so if we apply an even function first, so we do e of negative x and then take f of that, the e of negative x is just e of x, and then f of that is f of e1 of x. So then that turns out to be the same as the original function with just an x plugged in. So the composition of any function with an even function, where the even function is applied first, is an even function. Okay, so that gives you some some special things about particularly about even and odd functions, which really basically come down to symmetry. Okay, so in the next video, we're going to look at the area between curves. Okay, so hopefully we'll come back here to the next video in a bit.